Hi, we are from Group SEL. Today we want to present about our biomedical signal processing group assignment. My name is Solisan, and these are my group members Chan Wan Chong, Chan Ka Chun, and Gule Muhammad. First of all, I will introduce about electromyography. EMG is a technique that measures the electrical activity of muscles. These signals are produced during the contraction and the relaxation of muscle fiber as a result of their depolarization and repolarization. EMG signal can be captured using surface or intramuscular electrode. They are applied on various fields such as clinical diagnosis, rehabilitation, and physical therapy, human-machine interface development for controlling prostheses, and sport science to enhance performance and prevent injuries. To analyze EMG signal effectively, we use time frequency method since these signals are non-stationary, meaning their frequency component vary over time. Two widely used techniques are the short time Fourier transform and the wavelet transform. The short time Fourier transform divides the signal into short time windows for frequency analysis, but it has some resolution limitation. On the other hand, the Vector transform provides a multi-resolution approach, offering both time and frequency details simultaneously. This makes it ideal for EMG signal, helping us identify patterns like muscle fatigue and improve clarity by reducing noise.
First, we load the EMG data from the emg.mat file using function load. Then we define the signal properties include sampling frequency, sampling period, number of sample, and length of signal. Then we try to plot the EMG signal in time domain.
Therefore, based on the coding run, this is the display result of the EMG signal loaded. This plot shows the raw EMG signal where we can observe distinct bursts of activity. These bursts indicate the periods of muscle contraction and relaxation that reflecting the physiological activity captured by the sensor.
Then the analog EMG is shown in frequency domain using function FFT, which is fast Fourier transform. We only plot the signal in one side spectrum and half length because the result is symmetry.
We use the Fourier transform FT to understand the frequency content of the EMG signal. The plot shows a peak at 50 Hz, indicating this is the dominant frequency associated with the muscle activity.
Then we perform short-time Fourier transform with window size 200 millisecond and 5 millisecond. Window size is the number of samples in each window. Then overlap means 50-100 overlap between adjacent window, and an FFT function is the number of fast Fourier transform point. Next, the results are plotted using spectrogram.
The spectrogram provides a time frequency representation of the EMG signal with a 200 millisecond and 50 millisecond window. Later, I will explain about their difference.
Lastly, we apply continuous wavelet transform (CWT) to analyze time frequency characteristic of the EMG signal from a scaleogram.
Wavelet transform was used to provide an adaptive time frequency analysis of the EMG signal. Later, I will explain about the magnitude scaleogram. Based on the analysis, we know that the Fourier transform was applied to observe the signal's frequency content, while the STFT and wavelet transform were used for time frequency analysis. The STFT divides the signal into overlapping windows, whereas the wavelet transform adapts its resolution for better transient detection. And we know that based on the result given for the STFT, a 200 millisecond and 50 millisecond window with 50% overlap was selected to balance time and frequency resolution, while for the wavelet transform, the Morse wavelet was chosen to capture both high-frequency bursts and low-frequency trends. Based on these two results, we know that the 200 millisecond window provides smoother frequency representation, while the 50 millisecond window captures finer temporal details. Wavelet transform was used to provide an adaptive time frequency analysis of the EMG signal. This plot reveals transient high-frequency events while preserving low-frequency trends. Unlike STFT, the wavelet transform excels in capturing short-duration bursts and is ideal for analyzing transient phenomena. Based on the STFT results, for the 200 millisecond window spectrogram, it captures the overall frequency distribution with smoother transition. It is best suited for general frequency analysis, but lacks precise timing information for transients. While for the 50 millisecond window spectrogram, it provides finer time resolution, enabling clearer identification of transient bursts. It highlights rapid change in frequency components but sacrifices some frequency resolution. For the wavelet transform, the wavelet scaleogram displays high adaptability in capturing transient features across time and frequency, and it clearly highlights short bursts of high-frequency activity while preserving low-frequency trends.
In this section, we are going to discuss the strength and limitation of both the two techniques, short-time Fourier transform and wavelet transform. So, in short-time Fourier transform, it provides a clear representation of how frequency content change over time, ideal for non-stationary signal, and also it allows for localized analysis in both time and frequency domains. Actually, also, you have a choice in different window shapes to optimize analysis based on signal characteristic. So it's flexible for window function. The limitation of a short-term Fourier transform is the choice of window size because it affects both time and frequency resolution, leading to potential loss of detail. It also have a fixed temporal resolution, which means the window size might not effectively capture signals with varying frequency component. For if we look to wavelet transform, the strength of wavelet transform, it effectively analyzes signals at different scales, making it suitable for non-stationary signals. The adaptability also is another strength of wavelet transform, because if you see the various wavelet families like DBGs, HAR, it can be chosen based on specific signal characteristics, so allowing for a tailored analysis. The limitation is selecting the appropriate wavelet is crucial and also can be challenging as well. So the wrong choice might lead to poor signal representation or inaccurate results. If we apply a wavelet transform to a wavelet to a finite length signal, it can introduce distortion to the signal or artifact at the edges, and thus it complicates the analysis and interpretation. In conclusion, we successfully completed our project on processing and analyzing electromyography signals using advanced signal processing techniques, specifically focusing on a short time Fourier transform and wavelet transform. This method is provided us with effective tools for interpreting the physiological data inherent in EMG signals. The key findings: number one, the short time Fourier transform allowed us to visualize the frequency content of EMG signals over time, revealing important patterns related to muscle activity. However, its effectiveness was limited by the fixed window size, which could affect the time and frequency resolution. For wavelet transform application, it demonstrated a superior capabilities in analyzing non-stationary signals. Its multi-resolution approach enabled us to capture transit events and varying frequency components more effectively than short-term Fourier transform. This adaptability made it particularly useful for detailed analysis of muscle contraction. In a nutshell, for reflection, in this project we have learned how to perform short-time Fourier transform and wavelet transform using MATLAB. We also analyze and compare the spectrogram and scaleogram that come out from EMG signal. Then we discover the strengths and limitations of both short-term Fourier transform and wavelet transform in EMG analysis. For short-term Fourier transform, it provides information into frequency changes over time, while wavelet transform offered greater flexibility and precision for interpreting complex physiological signals. Thus, our findings enhance the understanding of muscle dynamics and suggest pathways for future research aimed at optimizing signal processing techniques in rehabilitation and neuromuscular assessment. Thank you.